Hi, I'm Gary Rubenstein. This is a warm-up session for a presentation I'm going to do in Denver called The Math Behind the Heavens and the Earth next week. I'm a teacher at Stuyvesant High School in New York City. I'm also affiliated with a great program called Math for America, which provided me funding to go to the conference, among other sorts of support. I teach astronomy to my classes for several reasons, but the most important is that the hardest thing about being a teacher is somehow getting your students to think about math outside of the math classroom. And after they learn about astronomy and how astronomy is related to why our shadows are a certain size and at a certain angle, different days, different times of year, why the moon looks different on different nights and appears in the sky different times at different places, and why the stars look different from night to night if we track them. Once you learn about astronomy, you can't help but think about these things every time you look up in the sky and see the moon or the stars or the sun or your shadow. You look up, you see the sun. You look down, you see your shadow. You can't avoid, at least subliminally, thinking about what you learned when you learned about astronomy in your math class. I have a website, GaryRubenstein.com, and on that you can get more details about what resources I used to learn about astronomy, in particular ancient astronomy. The biggest two resources were this book, History of Practice of Ancient Astronomy, and this website called the Nebraska Astronomy Applet Project. But go to the website, you can see more details about and links to these resources. When I teach my classes about astronomy, I start with a questionnaire. And these are questions that I found that a lot of adults don't know the answers to. Things like what causes the phases of the moon, or is it true that the days actually get longer in the summer, or is that some kind of illusion? What's the deal with Easter? Why is it sometimes early, sometimes it's in late March, sometimes it's in early April, sometimes it's in late April? Why is that? And different questions that I have here that, again, most adults don't know the answers to, and students sometimes know the answers, but even if they don't, it gets them motivated to learn them in the upcoming unit. When you look out in the sky, you see stars, as we see here, if it's clear, if you're in a place that doesn't have a lot of city lights. And a question that you should think about is, what happens if I watch the stars throughout the entire night? Now, the answer is it depends on what direction I'm looking in and what my latitude is. But here we are at 40 degrees latitude, which is New York City, and I'm looking out to the north. And I just wanted you to watch a little bit of this video. First of all, there are a bunch of constellations, and I'll get those up. So here's some constellations you might notice when you look up at the stars. The question is, what happens an hour later? Well, an hour later, the stars are going to look like that. They have shifted a bit. Some stars have moved a lot. Some stars have moved a little. An hour after that, they moved here. An hour after that, they moved here. And what you start to notice, if you watch for a while, is that the stars seem to be moving in circles. Some in very small circles, and some in large circles, all around a common center. Here it is again, and then sped up. So the stars seem to be going around this single star right here. That star is known as the North Star. If you superimpose a bunch of pictures of the stars at different times of night, you get a picture like this, which is pretty dramatic looking. Now, this is looking to the north. All the stars make circles, and some stars, particularly if you're looking to the south, make such big circles that the stars seem to rise and set because the circle is so large. Here are what the star trails look like when we're at the equator at night, and they have a different they look different. They don't move. They don't seem to be moving in circles, or they all seem to be moving in very large circles. And this is partly how they knew back in BC times that we lived on a sphere, because it would explain in part why these star trails would be different when I moved further north or south. Looking to the south, we see, on most nights, the moon at some time. Here is April 9th, 2013, looking to the south, the moon is there. It just was rising. It's midnight. There are some constellations here. There are 88 constellations, but the 12 most famous ones are the zodiac constellations. And the moon is situated inside of the constellation Libra. An hour later, the moon and Libra have moved together to be over here in the sky at 2 a.m., at 3 a.m., at 4 a.m. So throughout a given night, the moon and the stars seem to move together, and the moon seems to be moving along with the stars. But if we go to the next day, if we go almost 24 hours later, if we go to the next time that the constellation Libra is in this spot, look where the moon is on April 11th at around 4 in the morning. It's over there. It's not in the constellation Libra anymore, it's in the constellation Scorpio. And on April 11th at around 4 in the morning, the moon's here. And the moon's phase has changed. It's now we don't see as much of it. And April 12th at around 4 in the morning, the moon's here. It's a half moon. And April 13th, we only see a little crescent of a moon. So the moon, whereas everything seems to be going in circles from east to west, these constellations seem to be going very large circles, so they seem to rise and then set in the west. But the moon seems to be going slowly in the opposite direction, moving about 12 degrees a day. So about a month later, the moon ends up in Libra again. The sun is also puzzling because just before sunrise on about April 10th, the constellation Pisces was rising just before sunrise. But a month later, Pisces is already in the air or in the sky when the sun is rising, and the sun's in the constellation Aries. So when someone says, I'm an Aries, it actually does not mean that if you looked up the night they were born, you would see the constellation Aries. But really the sun, you really wouldn't be able to see Aries very well because the sun was in the constellation Aries. Actually, that was a long time ago when they named the constellations and did the astrology. The constellations have, in a sense, shifted. So when you were born, if you're in Aries, your sun was not actually even in Aries, but long ago it would have been. But that's what it means. It actually is the worst time to view the constellation because the sun is so bright that you can't see it. Now the planets, they noticed long ago that while the moon seems to be moving slowly or about 12 degrees a day from west to east, and the sun seems to be moving about 1 degree a day from west to east, the planets also this is Mars over a period of about 6 months, and notice how this is looking to the south. So it's moving on one day from here, it's going from west to east, just like the moon moves slowly each day and the sun. But then the moon starts moving backwards from east to west relative to the stars, and then finally back to west to east. When that happens, we say that the planet's in retrograde. It's going in sort of the opposite direction. Now that on a given night, the moon goes from east to west, just like everything else. But if you look on consecutive nights, it seems to make this sort of slow movement in this sort of loop. And any system of astronomy needs to explain this. The fundamental idea in astronomy is apparent motion. Apparent motion is if you see something, if you're moving, you're the observer and you're moving, you're rotating, you're revolving, whatever you're doing, and something else is either standing still or it itself is moving, the apparent motion is how the other thing seems to be moving from our perspective as if we were standing still. And a nice clip from a movie that illustrates this. That scene being from the 1980 movie Airplane. I have my students do an activity with apparent motion where I give them some scenarios, like here's a part of the sheet where person A is rotating and person B is revolving around them. This actually, I need to fix this. This is not, these pictures don't match with this scenario. And then my students actually go through and do this activity where they act it out. If you come to my presentation, I'll show you a clip of that, but as this is on the internet, I will skip by that. After I have my students experience apparent motion, then we start examining the different bodies in the sky, for instance, the moon. And the moon is often out during the day, which is puzzling to people. And also the moon changes phases from day to day, and these are two things we want to explain mathematically. To explain why we can sometimes see the moon during the day, it starts with why some people can see the sun and some people can't. So if I go over here, at any given time, half the people on Earth can see the sun, the people in this yellow area, and half the people on Earth can't see the sun. If I drew a line from the center of the sun to the center of the Earth, and I made a perpendicular line here, these people would be able to see the sun, these people wouldn't. The people in this spot see the sun right overhead. This is like on the equator, let's say. We're looking at top view of the Earth. The people here, well, if they're looking to the north, they see the sun to their right, just rising. And these people over here see the sun setting. Now the Earth rotates counterclockwise, so these people will eventually be over here. So they're at 6 a.m. Eventually they're going to be at 12 p.m. So half the people can see the sun, half the people can't. Likewise, if I draw a line from the center of the moon to the center of the Earth and draw a line perpendicular to that, what I see is that half the people on Earth can see the moon at any given time, and half the people can't. In this case, the people in the blue region can see the moon, and the people in the black region can't. Now the moon revolves around the Earth every 30 days, so right now the moon's kind of in this spot. And the people who can see the moon are from about 9 a.m. to 9 p.m. Let's see what happens as the moon moves. When the moon's over here, people from noon to midnight can see it. Over here, people from 6 p.m. to 6 a.m. can see it. And over here, people see it mainly during the day. There are basically 4 regions when I make those 2 lines. People who can see just the sun, both the moon and the sun, just the moon, or neither object. And I have my students actually, I give them configurations and we try to calculate what times the moon can be seen and when can it. Now to understand the phases of the moon, you can give your students all black and white cookies and have them rotated at different angles and then look at it from the side. So if we look at this cookie from the side, we see all white, kind of like a full moon or a full cookie. If I look at this cookie from the side, I see half white and half black. But if I look at this moon from this cookie from the side, I see a line that's mostly white and a little bit of black. And from that, you can get a sense of why the moon sometimes has these sort of unusual shapes, where you have a crescent shape, or most of the full moon is sort of filled in except for a small crescent. And it gives you a good picture for why that is. For my class, I made 3-dimensional models of the moon and have students walk around them to see how it looks. Here's how the moon looks, or here's how a sphere that's half white and half black looks when you rotate it around. You can really see that crescent shape right there. And there it is on the other side. Once you see this animation, anytime you see the moon in the sky, you start to see it as a sphere instead of this sort of crescent. Now, why does it make that shape? Well, here's a configuration. The sun's out here on the left, not pictured. And people who can see the moon will see a full moon because this part of the moon is all lit up. The Earth is not making a shadow on the moon because there's a little tilt to the orbit of the moon. Now look what happens as the moon moves. See, when it gets over here, people over here are looking at it at an angle, kind of like that cookie, where they see mostly white and a little bit of black. People over here get what's called a new moon. Now, you can't see it at night. First of all, you can't see it because at midnight it's on the wrong side of the Earth, but you can't even see it at noon because it's all that's up is the shadow part. A total solar eclipse can happen during a new moon, but it's pretty rare, again, because of the fact that the orbit of the moon is a bit tilted in relation to the plane that the Earth is going around the sun on. Now, I had my students do an activity where I gave them pictures of the moon in different days and had them make a graph of what percent of this middle line was white at any given time. So now it's about 80%. And let's see, as the moon goes around, if you make this graph up here, it makes a cosine curve. And I learned this activity from a Math in the Middle School magazine. So it's a great activity for getting students to have a cosine curve sort of appear in a very natural way in a real-life application, even if you don't call it a cosine curve. But if you're teaching higher math, you can actually prove that it's a cosine curve. All you need is this angle, TRM. And if you know that angle, it's possible to find the length of MG. There's a nice little right triangle here. MG ends up being R cosine theta. So when you add EF is also R cosine theta. When you add that to CE, which is 50%, you get the amount of if you know that angle, you could work out what percent of the moon is going to be white. And if you know what percent of the moon is white, you could figure out what that angle is. Back in BC times, Aristarchus tried to figure out how far away the moon was from the sun in relation to how far away the Earth is from the sun. By looking at a time when we have a half moon and the sun is just setting, we can see the moon pretty well. And I took this picture in Central Park, New York City. He estimated the angle between the moon and the sun to be about 87 degrees. So he made this picture. And nowadays, if this angle is 87 degrees, we say that CB is 1/19 of CB is 1/19 of AB, which makes the moon 19 times further from the sun as the moon is from the Earth, I should have said. Now, they didn't have cosine 87 back then. Instead, they had what are sort of can be thought of as pre-trig inequalities. Here we have a configuration where we have a right angle, AB is there, and I have this AD line segment, and then I extend it to get line segment AC. Now it turns out that the ratio of the two angles, this large angle BDA over BCA, is 1.75. But the ratio of the two hypotenuses, BC to BT, is less, it's 1.64. But the ratio of the two bottom sides there, AC over AT, is 2.01. And those relationships always stay true, that the ratio between the angles is always less than one ratio and bigger than the other. And with that, we're talking about like 300 BC. With that, Aristarchus was able to make this diagram and the estimation that the angle is 87 degrees and do this very involved proof, which you can show to your students as a way to make them appreciate very much the fact that we now can just say cosine of 87 degrees is about 1/19. He shows that it's between 1/18 and 1/20. Now, he was wrong about this calculation. It's really 1/400, but that's partly because his angle was not properly measured. It was more theoretical, really, but that angle should be close to about 89.5 degrees, somewhere around there. trying to locate where stars and planets and the moon are. And they're based a bit on our own longitude and latitude. So longitude and latitude are measured in degrees, which is maybe a little unusual because we think of latitude as how far north we are from the equator, but it can be measured as an angle, as you can see in this picture. This angle, when someone says I'm at 40 degrees latitude, they mean that if I were to make this angle where I have a point on the equator, center of the earth, and where I am, that angle is 40 degrees. And longitude is also measured in degrees, and it's going this way. So this point here that that longitude is measured from, it's called the prime meridian, and where it intersects the equator is sort of the 0 latitude, 0 longitude, and everything else is based on that. You'll see there's a similar way to describe where the stars are. In ancient times, they had a theory that the Earth was in the center of the universe, and the stars and the sun and the moon and the planets went around us on a giant sphere, and they were all, at least the stars were all sort of same distance from the Earth on the edge of this sphere. So it looks something like this. Everything was going from east to west. There's the sun on the sphere. There's a planet. It's Mars. There's the moon. Now, if you're located at 40 degrees latitude, things are still moving in those latitude circles, or it's still moving around the sphere, but things are rising and setting. If you stop the motion of the celestial sphere, you'll see that the stars stop, but the sun, the moon, and the planets, in this case, there's one planet, seems to be moving in the opposite direction. The moon's moving pretty quickly, 12 degrees a day. The sun's moving 1 degree a day. The planet there is moving, and take a look at this. The planet is the one thing that seems to be changing speed. It slows down, goes backwards, and then forwards again. And these are all things that they were able to explain with this celestial sphere model, and I'm going to talk more about that in future slides. When we have the celestial sphere, we can identify locations of stars, planets, the sun, the moon, using something that's kind of like longitude and latitude, but in this context, it's called right ascension for what's kind of like longitude, and declination for what's kind of like latitude. So there's this point that serves as sort of the starting point. It's called the vernal equinox, and I'll tell you what's so special about that point later. It's on what's called the celestial equator. Right ascension, which is actually could be measured in degrees, but they measure it in hours, where 1 hour is 15 degrees. And declination is measured in degrees. And this way of locating stars, or of describing the location of stars as if they're on this giant sphere, is still used today, even though it's not true that the stars are all on a giant sphere where every star is the same distance away from the Earth on this sphere. It doesn't matter. It behaves that way, and it's a good enough model for locating stars and describing their position in relation to the Earth. Another diagram you sometimes see when you're studying astronomy is something called the horizon diagram. And I'll show you what this is like. Here is the Earth inside the celestial sphere. And if I'm located here at 40 degrees latitude, located here, and to switch to what's called the horizon diagram, it will take my position, the little sort of circle that I'm standing on, and blow it up so it feels like I'm standing on a big flat circle, like that. And then if I rotate so that I'm horizontal, which is how I feel when I'm standing there, it looks like this. This horizon diagram, if I'm talking about a horizon diagram, everyone at a different latitude experiences sort of a different horizon diagram. Here's the North Pole and the celestial North Pole, and it's in a sort of different place depending on, it could be straight above me if I was at the North Pole of the Earth, and here it's kind of over here to the north of me. In horizon coordinates, it all depends on the, so here's me on my horizon, and if I want to locate something, I have two the latitude and longitude in this context are called the azimuth, which is kind of like longitude, how many degrees I am from north, and the altitude is kind of like the latitude of the star. But this is dependent on the observer, where they are, what their latitude is. And it also, unlike the celestial coordinates, these coordinates change throughout the night depending on what time it is. But they're useful. They have their use. A nice application that we can do with this celestial sphere model is figure out at night what our latitude is. Here's how that works. Directly above our own North Pole, which is what we're spinning on, there is a star which is called Polaris, or the North Star. And it's the star that doesn't move very much when we look at that star trail diagram. Somebody at the North Pole, if they look straight up, they would see that star. But here's somebody located at 70 degrees latitude. They're up here, close to the North Pole. But when they look straight up, they see point D. They would need to sort of look more to the north in order to see that North Star. Ironically, what's really happening is that we're rotating. It's making it look like all the stars are rotating around us, or revolving around us. We also revolve around the sun, but our revolution around the sun is so small in relation to all the stars that it doesn't affect this. The North Pole, the North Star is right above the North Pole, even when we move to different spots around our own sun. Our goal is to find angle ABC. And the angle we know is angle DCE, because we kind of look straight up. We don't see the North Star. We turn a little bit and we see the North Stars. We have to turn our heads 23 degrees in order to see the North Star. Well, this actually tells us our latitude. If you subtract 90 minus the angle we need to turn, it will tell us our latitude. And the reason why is angle DCE is an exterior angle. It's equal to the sum of this very small angle that's basically 0 because the North Star is so far away, plus this angle CBE. So if this angle is 23, this angle is also basically 23. And this angle, our own latitude, is complementary to that angle, so it will tell us our own latitude. Here I am at 40 degrees, so when I look up, I see this. I have to look about 50 degrees to see. I have to turn my head 50 degrees in order to see the North Star. That means this angle is about 50 degrees. It means this angle, CBE, is about 50 degrees, which makes ABC 40 degrees, which is my own latitude. Now, longitude is another story, and we actually can't use astronomy to find longitude. Ultimately, they solved the longitude problem by inventing a clock that kept very accurate time, and then they compared where the stars were compared to where the stars would be in a place that we know, and at what time it is there would help us find our longitude. So longitude is a whole book called Longitude about that story. I really like that book. Another thing you can do, once you know the latitude of two places that are on the same longitude line, you can use that information to figure out the circumference of the Earth. So here I have Chicago at 42 degrees latitude and New Orleans at 30 degrees latitude, and they are roughly on the same longitude line. The difference between them is 12 degrees. That means this angle is 12 degrees. We also know that the distance from Chicago to New Orleans is 830 miles. So using that, we can use a basic proportion. 12 over 360 equals 830 over x, and we get the circumference of the Earth to be 25,000 miles, which is accurate. Very long ago, around 250 BC, Aristarchus figured out a way to approximate the circumference of the Earth during the day by noticing that in two places on a certain day, the shadow cast by a stick was different lengths. So we have our two places, Alexandria and Cyan. And it's known on this day, which is known as the summer solstice, talk about that later, at noon there was no shadow formed by this stick. Now at the same time, in Alexandria, there was a small shadow formed by the stick. So if we imagine the sticks going into the center of the Earth, they would meet at the center of the Earth. Now they know the distance between these two cities is 5,000 stades, and which is a unit of measurement we don't use anymore, but I'll say more about that in a minute. Apparently it's about 559 feet. Now, knowing that this angle, because of the length of this little shadow that was formed, they approximated this angle here as 7.2 degrees, or 1/50th of a circle. Now, because of alternate interior angles, this angle beta is also 1/50th of a circle, 7.2 degrees, which means if you multiply this distance by 50, you get 250,000 stades, which is very close to the circumference of the Earth, but it depends how big you think a stade is, but even it's in the right range. So this was known all the way in 250 BC. Now some people have heard that in Columbus's time people thought the Earth was flat, but actually that's not true. They knew this. The Earth could not be flat, otherwise we wouldn't see different shadows at different latitudes. Columbus apparently used an approximation of the size of the Earth that was very small in order to get sort of funding for his mission. Actually, when he ran into America, he thought by their calculations that he had gone around the Earth, not just because he found land, but it agreed with what he was using as his estimate. A question that puzzles people every year that most people never get the answer to in their lifetimes is, why is Easter on different days in different years? And the answer is, it has to do with the lunar calendar. So it's known that the moon goes around the Earth every 29.5306 days, and that the Earth goes around the sun every 365.242 days. So what they did is so if there's a full moon on January 1st one year, there's not going to be a full moon on January 1st the next year, because 29.5306 does not go in evenly to 365.242. So they came up with a pretty good idea. You see, if you have a lunar calendar, after 12 lunar months, we have not actually made it around the sun, so we kind of have an issue. So they played around with throwing in a 13th month from time to time to make things work out. Ultimately, they figured out that if you multiply the number, if you take the 365.242 days and multiply it by 19 years is almost exactly the same as 235, I wrote months, which is a term I made up. So they have a 19-year calendar cycle that they invented, where every 12 years, 12 of the 19 years have 12 months, and 7 of the 19 years have 13 months. And in doing so, they have this 19-year cycle, and that's what the Jewish calendar is based on. So they have these leap months, 7 of them every 19 years. So the mystery of Easter is that it's based on this Jewish calendar. And so good trivia, Easter Sunday is always the first Sunday after the first full moon after March 20th, first day of spring. It's based on this lunar calendar from years ago. Next, I want to analyze what is happening with the sun. The sun not only seems to be going around the Earth once a day, but it also seems to be moving in relation to the stars. Well, also we have the days getting longer in the spring and the days getting shorter in the winter, so we need a model that describes all that. First, let's look at what is really happening. What's really happening is that we're going around the sun and we are tilted at a 23.5 degree angle. And as we move, we retain that tilt, so when we go around, it's kind of like that. Now when we rotate, in this case this is summer, we're tilted towards the sun, but look what happens when we rotate, how it looks to us. At summer, it seems to us, if we sort of straighten ourselves out, this is where the sun looks like it's up here to us, and when we rotate, it seems to go like that. When we switch to autumn, and then we get to winter here, at winter, it feels like when we rotate, it feels like the sun's down there, and when it goes around us, that's how it feels to us. And after winter, we get to spring. Now at spring, and this is a little tricky to see, even though we're tilted 23.5 degrees, there is a nice right angle here. It's not, our axis is not perpendicular to that plane that we're going around the sun. But if you drew a line from the center of the sun to the center of the earth, and then from the center of the earth to the North Pole, that would be a right angle. Spring equinox, and the sun would go around us, or we feel like the sun's going around us like this. That's called the spring equinox. And then eventually we get back to summer. That's what's really happening. What seems like it's happening is this. It seems like at spring, the sun seems to be going around us like this. And then, and this is how this fits into the celestial sphere model. So the sun's on the celestial sphere, it goes around us each day. But then each day it moves a little bit from west to east on this other circle, which is known as the ecliptic. And after a few days, the sun will now have moved over here. Its declination has gone higher, its latitude. And on that day, when it goes around the Earth, it goes around like this. This is how it seems. And then, here's the ecliptic again. When I get to summer, it's like the sun has moved up here. It goes around kind of like above us. And as the year goes on, the sun goes to autumn and winter. Here's winter. So each day it moves about 1 degree on that circle, but then it also rotates around each day like that based on its new sort of position, and finally back to spring. That's how they have this model of the sun being on the celestial sphere moving on this ecliptic circle. The ecliptic's really important because the sun seems to move on the ecliptic. The planets staying close to the sun are always located very close to the ecliptic circle. And the constellations, the 12 sort of most famous ones, are also on this ecliptic circle. And the sun seems to go through them, and the moon seems to go through them. And this is a really nice picture showing sort of what's going on. So the stars are kind of out here, and the sun slowly moves in this direction 1 degree a day, so it goes through the different constellations each day. In reality, we're tilted, and these constellations are the ones that are on sort of the plane of the on the plane of the sun's orbit. There's actually a third coordinate system called ecliptic coordinates, and for these we use the spring equinox. I can now define for you. It's officially the intersection of the ecliptic circle with the celestial equator, and that's the starting point for both the celestial coordinates. That's the right ascension and declination, and also it's the origin for ecliptic coordinates, where celestial longitude, I just described them wrong. Celestial longitude, when we say that, we're talking about the distance in this angle on the ecliptic, and celestial latitude is going this way. Now, the use of ecliptic coordinates is it's good for describing the position of the sun, because the ecliptic celestial latitude is always 0. It's also good for describing the position of the planets, because their celestial latitude is pretty close to 0. We'll see later that converting from one coordinate system to the other is not an easy thing to do. There used to be tool you could buy, or a globe type thing called an armillary sphere. You can still buy these, but most are antiques, where you can actually see that nice ecliptic circle here, and you could see where the positions and map out where things were. People used to have these things. They still exist in sculptures. Here's New York City, an Atlas sculpture, and you got that extra circle there being the ecliptic circle. Even this one, it's known that the Earth is very small in relation to the celestial sphere, so this would not be drawn to scale, but they have this extra circle, which I feel like is probably the ecliptic. That armillary sphere is very cool and very useful, and everyone has one. Everyone needs one, even the Wicked Witch of the West. So that's pretty cool. Now, the sun going around the ecliptic explains a bit of why days are sometimes longer at different times of the year. This is from the NAAP, that's the Nebraska Astronomy Applet Project. Really nice, useful website. So here I'm located at 40 degrees latitude using a horizon diagram. And on this day of the year, which is April 19th, you can see the sun going around its own latitude circle. And notice how it's kind of, more of that circle is above our horizon than below. You can really see it well here. So on this day, there's more than 12 hours of daylight and less than 12 hours of nighttime. If I move it to summer, to really high summer, and I encourage you to play around with these. So here I am in June, and wow, there's about 15 hours of daylight and only 9 hours of nighttime. You can really see how this circle is intersecting our horizon in such a way that it's more day than night. As the year goes on, we get to the autumn solstice, which is when we have 12 hours of daylight, 12 hours of nighttime. These two circles, they're both great circles, and they intersect each other. They bisect each other. And look at winter time. Look at this. If you live in the northern hemisphere and you look to the south in the winter time during the day, over a period of time, you see the sun has this little arc that it makes. So the question is it possible to calculate out how many hours of daylight there are? Well, there are two things you need to know. You need to know your own latitude, and you need to know the current latitude of the sun, otherwise known as the declination. So here I have, this is what it looks like when this big circle here is my 40 degrees, my horizon circle, and this other circle is the sun. And this is at the equinox, where the sun is actually at 23.5 degrees declination. And my goal is to find this angle here. That's going to require some auxiliary lines. Now, this is going to use some basic trigonometry. And ultimately, there's going to be a nice formula for how many hours of daylight for a given latitude and sun's declination. Here's a top view of this picture. Our goal is to find angle FOE. If I know that angle, I could use that to figure out what sort of percent of the circle this arc EDF is, which is how much nighttime there is. But I don't really know very much about it. I have this A is the radius of that circle, and X is this length GD, and I don't know much else beyond that. This is a side view of this picture. For this picture, I do know a couple of things. I know angle ARC, in this case, is 23.5 degrees. That's the sun's latitude or declination. I also know angle GRO. When we have the horizon diagram, the angle between us that we need to, when we look up, and the angle between the spot right above us and the North Pole, if we take the complement of that angle, we get our latitude, and that's related to why this is actually going to always be equal to our latitude. So for my scenario, this is 40 degrees, and this little guy is 23.5 degrees. That's the known information. Now, I have so much unknown information in this picture, but if I knew what A minus X was and what A was, I could figure out this angle by doing the inverse cosine of a minus x over a, and then I would double it, and I would turn that into a percent and multiply by 24 and subtract from 24. Well, that's great, except I don't know a or x, let alone a minus x over a. That's where the side view comes in. Angle C here is equal to angle ARC. These are parallel lines. Tan of C is B. I'm calling this OR B for now. Tan of angle C is B over A. Great, but I don't know what B or A is. As far as GRO goes, tan of GRO is A minus X over B, but I don't know what any of those are. But that's okay, because my goal was to get A minus X over A, and if you notice there's a B in the numerator here and a B in the denominator there, if I multiply them, the B's cancel out, and I learned that I could get A minus X over A by multiplying the tangent of the sun's declination by the tangent of my latitude. In this case, I get 0.3649. Once I have that, take the inverse cosine, double it, I get angle FOE is 137.2 degrees, run it through this percent, and learn that there are about 15 hours of daylight at 40 degrees latitude at the longest day, which is the summer solstice. Just so you know, there was a time where instead of describing people's latitude in degrees, they would talk about this is a place where the longest day is 15 hours, or this is a place where the longest day is 17 hours. So the further north you were, the longer the day was. But now with this sort of process, the students can calculate out how many hours of daylight there should be when you're at a given latitude with a given sun's declination. Now, finding the sun's declination is a bit tricky. It's 0 degrees at the summer and autumn solstice equinox. It's 23.5 at the summer solstice. It's negative 23.5 at the winter solstice. Other than that, it's a bit tricky to work out. So let's talk about that in some other presentation. It does not go nice and linearly. Because the sun is different on different days, that means that Indiana Jones would not have been able to conduct this experiment just by going there at a certain time, like they say in the movie, but he'd have to go there on a certain day of the year also. Now, they noticed long ago that the seasons do not all last the same amount of time. And this was disturbing to them. They felt like the sun goes around this ecliptic circle in a year, and that the Earth is in the center of this celestial sphere, and the sun is moving at a constant rate. And if all those things were true, all the seasons would be the same number of days. But they found that they weren't the same number of days, and this is still true, although it's different now than it was. Right now, summer and winter are actually longer than, summer and spring are longer than autumn and winter. So here's what it seemed like was happening. It seemed like it was going faster through winter and autumn, and you can see it's slower, faster. And they had to try to come up with a system that describes why this was happening. And this turns out to be one of the very first trigonometry problems. Either the sun is speeding up and slowing down, that's possible, but they didn't want to make that their theory. So they came up with another theory. Here's the breakdown. Now, spring's about 93 days, summer's a little more than 93 days, fall is a little more than 89 days, and winter is 89 days. That's how it is now. So how could that be if the sun's not moving faster? Well, maybe the sun just seems like it's moving faster because, and this is sort of pretty dramatic considering they came up with this in BC times, perhaps the sun only seems to be moving faster because the Earth is not located at the center of the ecliptic circle. So what if C is the center of, sorry about that, it gets confusing. C is the center of the circle, and here's the sun going around C, and the Earth is located not at the center, but over here. So what would happen, the sun's going around C, at a steady pace. But as the sun gets closer to the Earth, just like when a train gets close to us, it seems like it's going faster than when it's far away. Take a look. It will seem to go faster as it gets closer to us, and seem to go slower as it's far away from us. So that was a theory they had, and this is back in BC times, I don't know, like 200, 300 BC, and they had to basically invent trigonometry to figure out what's called the solar eccentricity. In other words, if O is not at the center of the circle, how far away is it? What percent of the radius is it? And to do that, they have this diagram where they want to know how big is segment CO if I know that this arc n to k is that happens in 92 days, 93 days. This one a little more than 93 days. L to M, 89, almost 90 days, and from M to N, that's winter, 89 days. So it became a really interesting trigonometry question. So they had to invent trigonometry. I want to take you through the calculation here. So the first thing we do is turn these sort of number of days into degrees. So Kn, which is spring, turns out to be that 91.46 degrees, and I have my other degrees here. And the goal is to figure out how big is CO in relation to the radius of this circle C. That's the solar eccentricity. And this picture is actually not drawn to scale because O is actually very close to C, but it isn't on C, and that's important. Let's see how we do this. First of all, NK and KL, which we both know, adds up to 183.74 degrees, but SK, that should say Q, is 180 degrees. And when I subtract those two things, hold on a sec. When I subtract those two things, I get 3.74 degrees, and because these two lines are parallel to each other, those angles are equal, those arcs QL and SN are equivalent, so QL is 1.87 degrees. Now, once I know how big QL is, if I draw in this line segment VL, which is the same length as CU, I can work it out with trigonometry. CL is the radius of the, CL is the radius, I'll just call that R. And using sine, R, we learned that VL, which is the same thing as CU, is R sine 3.74 degrees. And they had to invent trigonometry to get sine of 3.74 degrees, but they did, and they got it to be 0.03261 R. Now that we know the length of QL, arc QL, and we know the length of QP, which is 90 degrees, we can work out how big this little arc PK is. PK turns out to be 0.41 degrees. KW is this little line segment. It's the same as CT. It can be done if you know what sine of 0.41 degrees is. So they invented it and worked it out and learned that CT is 0.00717. If we then do the Pythagorean theorem, we learn that CO is about 0.0334 R, or the solar eccentricity is about 3% off of the center. So that was a really very important question about the way that the world works, and it was important enough to invent trigonometry pretty much for it. As I mentioned before, there are two main systems of locating points on the celestial sphere. One of them, and the most widely used one now, is based on the equator, the celestial equator, and you've got declination is kind of like latitude, and right ascension is kind of like longitude. But there's also this system based on, still has the same origin point, which is the vernal equinox, but now instead of going along the equator for your longitude, you go along the ecliptic circle, and that's just called celestial longitude, and there's also celestial latitude. Well, converting from one coordinate system to the other is a pretty involved process, and a lot of different cultures came up with ways to do that, and I want to show you how that works. It requires drawing a lot of auxiliary lines, at least one of the methods that I learned from this book, Heavenly Mathematics, that I liked a lot. So drawing in all these auxiliary lines, they get a picture that's something like this. This picture from Heavenly Mathematics shows that with all these auxiliary lines, we're able to get a relationship between the length of this arc that we want to get in degrees, the length of this arc in degrees, that's the declination, the length of this arc in degrees, and the length of this angle. We need to know this angle here, which is 23.5 degrees, because it's the ecliptic. Well, a neat thing about spherical trigonometry that I learned was that if you have an angle formed by two great circles like this, and you extend the arcs out so they go as far as like a quarter of a circle, this arc CB will actually have the same measure as this angle here, and in my presentation I have an extra slide that explains that a bit. Ultimately they end up with this formula. Sine of, we want to know what the declination is. We know the declination and we know this right ascension, and we want to know what the longitude is. Oh, sorry. We know the longitude and we want to know what the declination is. And this formula, sine declination, is sine longitude times sine of the ecliptic, gets you that. This kind of thing comes up so often in this sort of math that the very first log tables were not just logarithms of different numbers, but logs of sines of numbers, because you so often had to multiply together the sine of two different values, which is something we don't do so much. And in that other example, we multiplied together the tangent of two different values. Retrograde is when, over a period of days, a planet in relation to the fixed stars seems to be going from west to east, and then slowly for a little while from east to west, and then back from west to east. This happens because when the Earth is going faster than Mars, when it passes Mars, Mars seems to be getting closer to it. So take a look. Right now it's like Mars is going around a big circle around Earth. But as the Earth gets closer to it, look at what happens. Mars seems to slow down, stop for an instant. I paused it. Be going backwards and then going forwards again. So on the right-hand side, I have that right-hand side was how Mars seems to be moving in relation to Earth. If I pause this, let me pause it at a time where you could see both objects. So right now, Earth to Mars is this angle, and that's sort of the same distance and angle measure. And over here, you can see Earth getting closer. So this is the relative motion. Notice that Mars seems to make these loops. Well, in ancient times, they didn't know that Earth and Mars were both going around the sun like this. So instead, Ptolemy, who wrote a great book now called the Almagest, if that's how you pronounce it, he had an explanation. He said, what if the Earth is in the center of the universe and Mars is not going around the Earth? Mars is going around another circle called an epicycle, and that epicycle is going around Earth. Here's how this would look. And you see how it models the retrograde, which is pretty amazing. But it wasn't good enough. It made it a little bit too regular. So they could mess around with a few parameters, and I have this sketch that allows me to do that. You see, it makes it nice, way too regular. By messing around with a few things, one is the size of the epicycle, another one is the speed that the Mars is going around on that epicycle. And there's a third thing they ended up doing, because even those two fixes didn't improve things enough. They also moved the Earth off of the center of the circle, just like you saw before with the solar eccentricity. And that didn't fix it enough, so they added an extra point where the epicycle was moving around with constant speed of this third point, known as the equine point. So this is a pretty confusing series of compromises. But by messing around with the speed of the epicycle, the size of the epicycle, and the distance, these two distances are actually equal, they managed to get a very accurate modeling of the retrograde motion. Copernicus came along and he said that planets are going around the sun, and they're going at constant speed. And it was producing the retrograde loops, but again, they were a little too symmetrical. So Copernicus had to make some compromises also. One of his compromises is to make it so that the Earth is going around, actually the Earth isn't even going around the sun, it's going around something near the sun, and Mars is going around something else that, or Mars is going around the sun and the Earth is going around something near the sun. And this fixes things a bit. It makes those loops a little less symmetrical. But even that wasn't enough. So even Copernicus needed to add an epicycle, and a small one, and have Mars go around that epicycle by messing around with the size of that epicycle and the speed that it was going around it and these distances dc. Copernicus is finally able to get something that's about as good as Ptolemy, though not much better. It isn't until Kepler comes along that he fixes everything, has the planets go around the sun in ellipses, and has them actually speed up and slow down. A neat activity that I learned from Mathematics Teacher magazine, 2 different issues, is how you can work out how far the other planets are from the sun, and also what their orbital periods are. So here's Earth, Mars, and Jupiter. This is easiest to understand for the planets that are outside of Earth's orbit. Here's what's really going on. Earth is moving fastest, Mars is moving slower, Jupiter is moving the slowest. In order to work out how long it takes for Mars to go around the sun, all we need is to know 2 things. So I'm going to zoom out. First thing we need to know is what's called opposition. That's when the sun, Earth, and Mars are all in this nice straight line. You know you're in opposition with Mars when at midnight Mars is sort of at its sort of highest point in the sky. So at midnight these people would see Mars right above them. Now we wait for an opposition to happen, and then we start counting, and we wait till the next one happens. And take a look, it will happen at around 780 days approximately between oppositions. Well, that's all I need. That's the only number I need, because take a look what I can do now. 779 days turns out to be 2.13 Earth years, because I know that Earth year is 365.25 days. But because Earth lapped Mars, it's 1 less of Mars's years. It's only 1.13 Mars years. So we subtract 1 from the number of Earth years, and then we set up a proportion. 1.13 to 2.13 is 1 over x, and we solve for Mars's year to be 1.88 years, or 688.5 days. And you could do a similar thing I'll show you for Jupiter. Now, as far as figuring out how far Earth is, or Mars is, from the sun, well, if we measured the amount of days from that opposition we had before until a different event, which is happening soon, right here, 107 days after that opposition, we have Mars in what's called quadrature. Quadrature happens when these people at 6, so right at sunset, at 6 p.m. At 6 p.m. at sunset, we can see Mars directly overhead, or people at midnight here are seeing Mars sort of setting in the west. Either way, it's 107 days before that happens. This produces, so when that happens, we have a right angle. And anytime we have a right angle, we can have a right triangle. And if we have a right triangle and some angles, we can work out using trigonometry. So 107 days is 29% of a year, which is 105 degrees of Earth's orbit. So from here to here is 105 degrees. But we calculated that Mars's year is longer, 689 days. That's only 16% of Mars's year, so that means this angle here is 56 degrees. Subtract those 2 angles, and we get 49 degrees. This gives us a 49-degree angle here, and we can do trigonometry now. Use cosine of 49. We're calling the distance from Earth to Sun 1 astronomical unit for now, and we were able to calculate out that it's 1.5 astronomical units from Mars to the Sun, which is true. Now, we now know that the Earth is 93 million miles from the Sun, but they didn't know that until almost 1700. Up until then, they just would say everything had to be done in relation to distance to the Earth. You could read a nice book called Planets, I think it's called The Planets, where they describe about how they figured out finally how far the Earth is from the Sun. These two calculations can also be done for Jupiter. So here's Jupiter. Opposition to opposition is going to happen more quickly because Earth is going faster than Jupiter. Oh, here's quadrature. That happens after only 89 days. And if we go around, we'll see that Earth catches up to Jupiter faster. It doesn't take 2 years. It just takes a little bit more than 1 year because Jupiter is moving so slow. 399 days. So to figure out how long Jupiter year is, 399 days is 1.09 Earth years. It's only 0.09 Jupiter years. Set up a proportion to work out that Jupiter is about 12 years to go around. Likewise, 89 days to quadrature is about 87 degrees of Earth's orbit, but it is only 7.6 degrees of Jupiter's orbit, and our right triangle tells us that Jupiter's distance from the Sun is 5.8 times the distance from Earth to the Sun, which is pretty accurate. Now, when Kepler came along, he figured out that the Earth goes around the Sun it's an ellipse, and the Sun's at one focus of the ellipse, and the Earth actually does speed up and slow down. It speeds up as it gets closer and slows down as it gets further away. This ellipse is very eccentric. The real one has a very small eccentricity, very close to zero, but this is exaggerated. He also came up with what's called the equal area law, which says that here's the Earth in two different, like a month apart, and this wedge has a certain area, and as time goes on, the Earth slows down here in such a way that the area of this wedge is the same as the area of that other wedge. So it's called the equal area law. It slows down so that it needs to slow down so that this area stays the same. Here it goes faster because we have this sort of bigger height of this triangle. Pretty cool. Kepler also figured out a relationship between the square of the time it takes to go around the Sun versus the cube of the distance. Now, Kepler was not perfect in searching for reasons why the planets are the distance they are from the Sun. He came up with a theory that was not true, but it was still mathematically interesting, and this picture is a great picture. It has, you see platonic solids, you see a cube and a tetrahedron, and inside here is a dodecahedron, and inside there. So I want to explain about this picture because it's something that students can, even though it turned out to be completely not true, it still is interesting math. Kepler thought there were six planets at the time, and there's only 5 platonic solids, so by putting inscribed and circumscribed spheres around them, he found that it was very close to the size of the planetary orbits. So here's the way this works. You start with a sphere to represent Mercury's orbit and put an octahedron perfectly around that. And around that octahedron, you put a sphere, and it turns out that the ratio between those spheres is very close to the ratio of Venus's orbit size to Mercury's orbit size. Put an icosahedron around that sphere, and a sphere around that icosahedron, and the ratio between those spheres is very close to Earth to Venus's distances. Put a dodecahedron around that sphere, and a sphere around that dodecahedron, and you find that the ratio of those spheres is very close to the ratio of Mars to Earth's orbits. Shrink this guy down, put a tetrahedron around that sphere, and a sphere around that tetrahedron, And the ratio of those orbits ends up being close to the Jupiter and Mars ratio. And finally, stick a cube around that sphere and a sphere around that cube, and the ratio of those spheres is close to Saturn to Jupiter. So this was completely incorrect, but it's still interesting, and you could actually have your students try to work out these ratios. I found the cube one to be the only one that was kind of relatively easy. I'm going to conclude this presentation with an explanation of how Isaac Newton in the 1600s gave a sort of proof of the equal areas law. Now, the equal areas law says that as the planet moves, it sweeps out, if you let it sort of made a triangle or some kind of shape, it sweeps out equal areas in equal times. And this seems like a very difficult thing to do, but Isaac Newton showed how it could be described by using the idea of gravitational pull. In other words, we have here a planet at point A, and if there was no sun, the planet would move towards point B at a certain speed. If the sun were not exerting any force on it, the planet would just sort of go in a constant speed in that direction. So if there was no sun, in the next period of time, the planet would go from B to C. So without the sun, this would be our situation. And the area of triangle SAB is equal to the area of triangle SB, lowercase c. I'll show you why that is in a minute. But that's if there was no sun. But there is a sun. And what happens with the sun is that when the planet gets to B, instead of going to C, now the sun's constantly pulling the planet in towards it. But we're going to imagine for a minute that the sun only exerts its force at like time intervals, like every few seconds it does like a pulse where it pulls the planet in towards it. So the planet is trying to go, it just went from A to B, it's planning to go from B to C, all its momentum is going this way. But what happens is that the sun pulls it in when it gets to point B. And it pulls it in at a force that's magnitude is the length of BF. So the sun wants to go from B to lowercase c. The sun wants to pull it in from B to F. Well, we teach our students that when you have two forces like that, the acting on an object, the object doesn't, it goes on the diagonal of the parallelogram formed by those two things. So the planet wants to go to lowercase c, the sun wants to pull it to F, and instead the planet goes towards point capital C, which looks like that. And that creates a triangle like this. And I'm going to show you how to prove that that triangle, BCS, has the same area as the original triangle, ABS. All three of these triangles end up having the exact same area, 3.94 centimeters, shows that the equal area law is true, at least in this simplified case where the sun kind of pulls in the object at like time intervals, does like a pulse of pulling it in. But then if you could imagine speeding it up so the pulses are more regular, it turns into more of a curve. So Newton's explanation of this picture, there should be a letter A down here, not a C. These two triangles are same area because they have the same base. C, capital CB is the same length as capital B lowercase c. And these triangles actually have the same height. If I drew it in, it would be some kind of like a perpendicular going from here to around here. So these two triangles have the same area. Now if I look at the second triangle and the third triangle, they also have the same area because SB is the base of both of them, and because B lowercase c is parallel to DC, D capital C, these lines are parallel, so sort of the heights the heights are defined, or the distance between these two parallel lines. So these two things have the same area, and that makes the first triangle, the original one, SCB, have the same area as the third one. SAB has the same area as SB capital C. And if you continue this over and over, With the sun, the planet goes from here to here. The sun pulls it this way. It changes the planet's direction to go sort of diagonally. The sun pulls it again. The planet goes this way. And you can see how the planet might go around the sun in some sort of a curve. Now, why is that curve an ellipse? Well, I'm just going to show you a diagram, which you can, if you're interested in, you could watch a video I once made about this. In 1630s, Newton wrote something called the Principia, where he proved that if the planets go around the sun in an ellipse, it would mean that the sun's force must be equal or proportional to 1 over the square of the distance the planet is from the sun. And this awesome diagram with an ellipse and all these lines, well, I made an 80-minute video just trying to explain how this works. I just wanted to leave you with that. If that's something, it uses, believe it or not, just basic, well, I should say basic, it uses geometry, and it uses some obscure theorems about ellipses that aren't known nowadays, but it's pretty cool, and you'll feel good about yourself when you fully understand it. So that's my presentation. I have an email address, I have a blog that I write, I'm on Twitter, I have a YouTube page. This presentation is on YouTube, and the files you can find at GaryRubenstein.com, NCTM 2013.